Welcome to the chapter Real Numbers.
This slide presents the overview of the chapter. Learning objectives. By the end of this chapter, you will be able to
find the rational numbers between two numbers using mean method. Examine the irrational numbers. Represent the irrational numbers on a number line. Explain the real numbers. Represent the real numbers on a number line. Evaluate the operations on real numbers. Know how to rationalize the denominator. List the laws of exponents for real numbers. Explain the concept of surds.
Introduction. Before entering into the chapter, follow the instructions shown on the screen. Click each tab to know more.
In previous classes, we learnt about natural numbers. These are the positive integers from 1, 2, 3 and so on. It is denoted by n. Whole numbers. The whole number is a number that has no fractional part like 0, 1, 2 and so on. It is denoted by w. Integers. It is the collection of negative numbers and whole numbers like -2, -1, 0 and so on. It is denoted by z. Rational numbers. A rational number is one that can be represented as the ratio of two integers like -2, -1, -5/3 and so on, where denominator is not equal to 0. It is denoted by q. Do you know how to find rational numbers between two numbers using mean method and how to represent irrational numbers on a number line? And do you know how to rationalize the denominator? Here, in this chapter, let us know how to represent rational and irrational numbers on a number line, and also about rationalizing the denominators and different types of laws of exponents for real numbers. Representation of whole numbers on a number line. To represent whole numbers on a number line, initially mark the point 0 on the line. Then, by setting equal distances, the right side of 0, we plot numbers like 1, 2, 3 and so on. Representation of integers on a number line. The integers number line is the same as representation of whole numbers on a number line, but here, to the left side of 0, the negative integers like -1, -2, -3 and so on are plotted. Now, let us learn about representation of a rational number on a number line. For example, let us consider the number 10/2. Here p is equal to 10 and q is equal to 2, where p and q are integers and q not equal to 0. Here the number 10/2 can also be represented as 5/1. Similarly, let us consider one more example, that is 16/24. Further simplification is as shown on the screen. So all these are equivalent rational numbers. Thus, from examples 1 and 2, we conclude that the rational numbers do not have a unique representation in the form p/q. And also we observe that the rational number of the form p by q, assuming q naught equal to 0, and that p and q doesn't have common factors other than universal factor 1. So, on a number line, among all the infinitely many fractions equivalent to the given number, we use simplest form to represent all of them. In the given fraction 2 is the numerator and 3 is the denominator. From image 1, let's see the pictorial representation of 2 by 3. It means that from 3 equal parts, 2 parts are taken out as shown in the below image. Representation of 2 by 3 on a number line is as shown in image 2. Let us represent 2 by 3 on a number line. Initially draw a line. Take a point O on it and mark it as 0. From the right side of point O, set off equal distances to A, that is OA. Now divide OA into 3 equal parts as denominator is 3. Let OP be the segment consisting 2 parts out of 3. Thus, the point P represents the rational number 2 by 3. And similarly, for representation of rational number minus 2 by 3, set off equal distance to the left side of O, that is OB. And then divide OB into 3 parts. The segment OP' consists 2 parts out of 3. Thus, the point P' represents the rational number minus 2 by 3. Let us discuss how to find the rational numbers between any two numbers using mean method. Mean method is categorized into 2 types, namely method 1 and method 2. Click each method tab to know more. Method 1. If p and q are two rational numbers, then its mean is p plus q by 2. Let us consider the two numbers 2 and 3. Here p is equal to 2 and q is equal to 3. Then the mean of these two numbers is 5 by 2, which lies in between 2 and 3. If further the process is continued, we obtain many more rational numbers in between 2 and 5 by 2 as shown below, where 2 is less than 9 by 4, less than 5 by 2, less than 3. Method 2. Let us consider the same numbers used in method 1. Here, to find 4 rational numbers between 2 and 3, we write 2 and 3 taking denominator as 4 plus 1 is equal to 5. That is, 2 equal to 10 by 5 and 3 equal to 15 by 5, which is further expressed as shown on screen. Note: thus, we conclude that there exists infinitely many number of rational numbers in between any two given rational numbers. Let us solve some example problems on converting rational numbers to decimal form. Express 8 by 3 in the decimal form by long division. Solution: by dividing 8 with 3, we get as follows. Express 17 by 8 in the decimal form by long division. Solution: by dividing 17 with 8, we get as follows. Therefore, 17 by 8 is equal to 2.125, which is a terminating decimal. Express 0.84 bar as a rational number, P by Q form. Solution. Let x is equal to 0.84 bar, which is represented as equation 1. Multiplying equation 1 with 100 on both sides, we get as equation 2. Subtracting 1 from 2, we obtain as follows. Therefore, P by Q form of 0.84 bar is 28 by 33. Let us have a look on irrational numbers. Let us consider the equation x square equal to 9. Solving this equation, we obtain x values as -3 and +3. Now, we know the representation of the numbers -3 and +3 on a number line, which is as shown. Similarly, let us take the equation 2x equal to 5. Here we obtain x value as +5 by 2, and the representation of it is as shown. Finally, let us consider the equation x square equal to 3. Taking square root on both sides, we get as shown on screen. Thus, x value is obtained as √3. Such type of numbers can't represent on a number line directly. For this, we need to know the value of √3. So, let us find √3 value by long division method. Let us solve an example of irrational numbers. Find the value of √3 by long division method. Step 1. Place decimal point after 3. Step 2. After decimal point, write zeros and pave them putting bar over them. Step 3. Find the largest square smaller than 3, that is 1. Subtract 1 from 3, which leaves 2, and write 1 as the first digit of the quotient. Step 4. Take the remainder 2 and bring the first pair of zeros to down, and then add a decimal point to the answer. Then follow the same steps to find the next digits. Step 5. Now take the first digit of quotient 1, but make it double, that is 2, and make that number 10 times. Then take a number of your wish, say 7, and it must be less than 200. As in the example, product of 27 and 7 is 189, which is less than 200. Step 6. Subtract 189 from 200, which leaves 11, and bring the pair of zeros to down. So, here the value of root 3 is 1.732 and so on. Let us know in detail about irrational numbers. The irrational numbers, like root 3, by solving we obtain the value as non-terminating and non-recurring decimal. Thus, we conclude that the decimal number is either terminating or non-terminating recurring decimal, which can be expressed in the form of p by q, is known as rational number. As here, the number root 3 is non-terminating and non-recurring decimal. So, here we can't express root 3 in terms of bar. Hence it is known as irrational number. And such type of numbers cannot represent in terms of p by q. In short, the non-terminating, non-recurring decimals are also known as irrational numbers and are denoted by S or Q dash. The above table describes some root values. From the table, we observe that if n is a natural number other than a perfect square, then root n is an irrational number. Thus, we identify root 1 and root 4 are rational numbers, and root 2, root 3, root 5 are irrational numbers. Let us see a brief introduction to irrational numbers. In 5th century BC, famous mathematician and philosopher Pythagoras and the Pythagorean in Greece were the first persons to introduce the numbers which are not rationals, that is, irrational numbers. Initially, Pythagoreans proved that root 2 as a rational number. Then after, Theodorus of Cyrene proved that root 3, root 5, root 7, root 9 and so on are also irrational numbers. About pi. Pi is defined as the ratio of the circumference c of a circle to its diameter d, that is pi equal to c by d. As pi is in the form of ratio, there is no common unit to measure the circumference c and diameter d of the circle. Either c or d should be irrational if we want to measure accurately. So pi is regarded as irrational. The Greek genius Archimedes first computed the value of pi, and he showed the value of pi lies between 3.140845 and 3.142857. The great Indian mathematician and astronomer Aryabhatta, 476 to 550 AD, found the value of pi correctly to 4 decimal places, that is 3.1416. Pi equal to. The decimal expansion of pi is non-terminating and non-recurring. So pi is an irrational number. An approximate value of pi is 22 by 7. Albert Einstein was born on March 14, 1879, and the same day it is celebrated as Pi Day. Now, let us learn how to represent irrational numbers on a number line. Before going to learn the representation of irrational numbers on a number line, we need to know about Pythagoras Theorem. The Pythagoras Theorem states that in a right-angled triangle ABC, the line opposite to the right angle is hypotenuse, and it says that hypotenuse square is equal to the sum of the squares of other two sides, that is, as shown on screen. Now, let us go back how to represent the numbers with roots on a number line. Here, let us represent root 3 on a number line. Initially, draw a number line, mark point 0 on it. Either sides of 0, mark the points -2, -1, 1, 2 with equal set of distances as shown. Now, with the same distance from 0 to 1, draw another line with right angle at 1 and then join these points as shown. Let us mark the points of right angle triangle as OAB. Now, to find the distance between OA, we use Pythagoras Theorem. From Pythagoras Theorem, OA is equal to square root of OB square plus BA square, which is equal to square root of 1 square plus 1 square, that is root 2. So, the distance between OA is root 2. Now, draw the perpendicular line to OA of unit length and mark it as D. Now, join OD. Then take OD as radius, that is length of root 3, and construct a circle such that it meets the number line and mark the intersecting point C. So, the OC is also radius of the circle, which is the representation of root 3. Now, let us discuss about real numbers. Rational numbers. The numbers which can be written in the form of P by Q, where P and Q are integers and Q not equal to 0, are known as rational numbers. Irrational numbers. The numbers which cannot be written in the form of P by Q, where P and Q are integers, are known as irrational numbers. The combination of rational and irrational numbers is known as real numbers. Now, let us observe the conversation on real numbers. Hi Raju. Hi Venkat. I have one doubt in real numbers chapter. Can you clear it? Yeah, for sure. On a number, if we represent all rational and irrational numbers, will there be any numbers which are not covered in the number line? No, Venkat, as we know that the combination of all rational and irrational numbers are called real numbers. So these real numbers cover all the points on a number line. And there will be unique representation of real numbers on a number line. Hence it is also known as real number line. Can you give some examples? Yeah, some of the examples of real numbers are -4, 0, 1, pi, root 9 and so on. Now, let us solve some example problems on irrational numbers. Find two irrational numbers between 0.12 and 0.13. Solution. Let the given numbers be a equal to 0.12 and b equal to 0.13. We observe that the given two numbers are irrational numbers and a less than b. Since by comparing both the numbers after the decimal point, the first digit is same in both the cases, and the second digit of 2 is lesser than 3. Now, let us write some numbers such that greater than a and lesser than b. They are 0.121, 0.122, 0.123. Now, add some non-terminating recurring decimal to these numbers as shown on screen. Let us assume these numbers as C, D, E. Thus, we conclude that the numbers C, D, E are irrational. Therefore, A less than C, less than D, less than E, less than B. Find two irrational numbers between 3 by 2 and 7 by 2. Solution. Let the given numbers be a equal to 3 by 2 and b equal to 7 by 2. We observe that both the numbers are rational since they are in the form of p by q, where q not equal to 0. Initially here, we need to find the decimal expansions of the given two numbers. The decimal expansion of 3 by 2 is 1.5. And similarly, the decimal expansion of 7 by 2 is 3.5. Now, represent the two decimal numbers on a number line. The irrational numbers between these two numbers should lie in between 1.5 and 3.5. So, let us consider some numbers like 2, 3. By adding some non-terminating, non-recurring decimal to these numbers, we get two irrational numbers. Find an irrational number between 4 and 6. Solution. If a and b are two positive rational numbers such that ab is not a perfect square of a rational number, then root ab is an irrational number lying between a and b. Therefore, an irrational number between 4 and 6 is root of 4 into 6. By solving further, we obtain it as 2 root 6. Let us do an activity on constructing the square root spiral. Take a large sheet of paper, pencil and scale. Mark point O on it and draw a line segment OA of 1 unit length. Now draw a line segment AB perpendicular to OA of same 1 unit length. Joining OB using Pythagoras Theorem, we know the distance between OB is equal to root 2. Again, draw a line segment BC of unit length perpendicular to OB. Join OC where OC equal to root 3. Draw a line segment CD of unit length perpendicular to OC. By continuing the same process, finally we obtain the spiral made of line segments as shown on screen. Note that the line segment OA, OB, OC, OD and so on represents the lengths root 2, root 3, root 4 and so on respectively. Representation of real numbers on the number line through successive magnification. Visualize 3.765 on a number line using successive magnification. We know that 3.765 lies between the interval 3 and 4. To have a rough idea for locating it on a number line, make 10 equal parts and mark them as 3, 3.1, 3.2 and so on up to 4 as shown. Now look the portion in between 3.7 and 3.8 using magnifying glass and realize that 3.765 lies between 3.7 and 3.8 as shown in figure 1. So, let us now divide this portion into 10 equal parts and represent them as 3.71, 3.72, so on 3.8 as shown in figure 2. As before, now we can visualize through the magnifying glass that 3.765 lies in between 3.76 and 3.77. So, let us focus on this portion of number line as shown in figure 3 and imagine to divide it again into 10 equal parts. Thus magnify it to see it better as in figure 3. This is how the terminating decimal expansion on a number line is represented. Now, let us represent non-terminating recurring decimal on a number line. Visualize 4.26 bar on a number line using successive magnification. Here, the repeating decimal 4.26 lies between the interval 4 and 5. To have a rough idea for locating it on a number line, make 10 equal parts and mark them as 4.1, 4.2, so on up to 5 as shown in figure 1. Now, look the portion in between 4.2 and 4.3 using magnifying glass and realize that 4.26 lies between them as shown in figure 2. So, let us now divide this portion into 10 equal parts and represent them as 4.26, 4.261, so on up to 4.27 as shown in figure 3. As before, now we can visualize through the magnifying glass that 4.2626 lies in between 4.262 and 4.263. We can proceed endlessly in this manner and simultaneously imagine the decrease in the length of the interval in which 4.26 bar is located. Operations on real numbers. In the previous class, we learnt about properties of addition and multiplication, and we also know how to add, subtract, and multiply the given rational numbers. Now, let us discuss how irrational numbers are also closed to fundamental operations. Let us solve some examples. Here, in the first example, the addition of root 6 and minus root 6 results 0, which is a rational number. In the second example, the difference or subtraction of root 7 and root 7 results 0, which is a rational number. In the third example, the product of root 4 and root 4 is 4, which is a rational number. Finally, the division of root 3 and root 3 is 1, which is also a rational number. From the above 4 examples, we conclude that the sum, difference, quotients, and products of irrational numbers need not be irrational numbers. Thus, the irrational numbers are not closer to fundamental operations like addition, subtraction, multiplication, and division. Let us list out some types of properties which are useful in various ways. If a and b are positive real numbers, then root ab is equal to root a into root b. Root a by b is equal to root a by root b, where b not equal to 0. Root a plus root b into root a minus root b is equal to a minus b. A plus root b into a minus root b is equal to a square minus b. Root a plus root b into root c plus root d equal to root AC plus root AD plus root B C plus root BD. Root A plus root B whole square is equal to A plus 2 root AB plus B. Let us solve some example problems using the properties of irrational numbers. Evaluate 5 plus root 3 into 5 minus root 3. Solution given. As it is of the form A plus root B into A minus root B, it can be written as A square minus B. By further solving, we get as 5 square minus root 3 whole square, that is equal to 25 minus 3, which in turn equal to 22. Note, if A is rational and B is irrational number, then A plus B, A minus B, A into B and A by B, where B not equal to 0 are irrational numbers. Evaluate root 3 plus root 4 whole square. Solution given. As it is of the form root A plus root B whole square, which is equal to A plus 2 root AB plus B. By further solving, we get root 3 whole square plus 2 into root 3 into root 4 plus root 4 whole square, which is equal to 3 plus 2 root 12 plus 4 in turn equal to 7 plus 2 root 12. Subtract 2 root 4 plus 3 root 5 from 6 root 5 plus 5 root 4. Solution. When we subtract 2 root 4 plus 3 root 5 from 6 root 5 plus 5 root 4. By further solving, we get 3 root 5 plus 3 root 4. Rationalizing the denominator. We already learned that we cannot locate irrational numbers on a number line directly. To locate the irrational numbers on a number line, we need to find the value of the given irrational number. Suppose, consider the irrational number 1 by root 5. To locate it on a number line, initially we need to find the value of it. In order to find the value of 1 by root 5, we cannot divide the value of root 5, that is 2.236, with 1. It is not easy to find the value of 1 by root 5. In such cases, change the denominator into a rational form. Here, to rationalize 1 by root 5, multiply numerator and denominator with root 5 as shown on the screen. We obtain it as 1/5 of root 5. So, now we can plot root 5 by 5 on a number line. Thus root 5 is the rationalizing factor of root 5. Similarly, the product of root 5 and root 5 is 5. Here root 5 and root 5 are rationalizing factors of each other. Note, if the product of two irrational numbers is a rational number, then each of the two numbers are rationalizing factors of each other. Rationalizing factor of a given irrational number is not unique. Let us solve some example problems on rationalizing the denominator. Evaluate 3 by root 5 minus 2. Solution. Given expression is 3 by root 5 minus 2. Multiplying numerator and denominator with root 5 plus 2. We get as shown. Multiplying it further, we get as 3 into root 5 plus 2 by root 5 minus 2 into root 5 plus 2. Since here, the denominator is in the form of a minus b into a plus b, we can write it as a square minus b square. Thus, it is expressed as 3 root 5 plus 6 by root 5 square minus 2 square. By further solving, we get as 3 root 5 plus 6. Evaluate 8 plus root 2 by 2 minus root 2. Solution. For the given expression, multiplying numerator and denominator with 2 plus root 2, we get as follows. Let us discuss about laws of exponents for real numbers. The laws of exponents are product rule. Product rule is defined as a power m into a power n equal to a power m plus n. Power of a power. Power of a power rule is defined as a power m whole power n is equal to a power mn. Power of a quotient. Power of a quotient is defined as a power m by a power n equal to a power m minus n. Power of a product. Power of a product is defined as a power m into b power m equal to ab whole power m. Zero exponent. Zero exponent is defined as a power 0 equal to 1, where a is not equal to 0. Negative exponent. It is defined as 1 by a power m equal to a power minus m. Click each tab to know more. For example, let us consider 5 power 6 into 5 power minus 6. Using laws of exponent, we can write it as 5 power 6 plus minus 6, which is equal to 5 power 0, in turn equal to 1. For example, let us consider 6 power 3 whole power minus 1, which is equal to 6 power minus 3. It can be written as 1 by 6 power 3, which is further equal to 1 by 216. For example, let us consider 10 power minus 6 by 10 power 3, which is equal to 10 power minus 6 minus 3, in turn equal to 10 power minus 9. For example, let us consider 5 power 2 into 10 power 2. As powers are same, it can be written as 5 into 10 power 2, that is equal to 50 power 2. For example, 3 power 0 is equal to 1. For example, let us consider 1 by 2 power 3, which is equal to 2 power minus 3. Let us solve few example problems on laws of exponents. If 4 square equal to 16, then prove that square root 16, which is equal to 4. Solution. Given that 4 square equal to 16. By further solving, we get as shown on screen. If 11 square equal to 121, then prove that square root 121 equal to 11. Solution. Given that 11 square equal to 121, by further solving, we get as shown on screen. Note: if a power m is equal to b, then mth root b is a. Mth root of b is a. Mth root b is equal to b power 1 by m, which is equal to a power m whole power 1 by m, that is equal to a. So, assume m be a positive integer, where a greater than 0 be a real number. If b power m is equal to a for some positive real number b, then mth root of a is b, which can be written as mth root a equal to b. List of laws of exponents. If a greater than 0 be a real number and let u, v be irrational numbers, then we have types of laws as follows. A power u into a power v is equal to a power u plus v. A power u whole power v is equal to a power uv. A power u by a power v is equal to a power u minus v. A power u into b power u is equal to ab whole power u. Uth root a is equal to a power 1 by u. Let us discuss about surd. A number that can't be simplified to remove a square root or cube root etc. is called surd. If n is a positive integer greater than 1 and a is a positive rational number but not nth power of any rational number, then nth root a, or a power 1 by n is called a surd of nth order. In general, we say the positive nth root of a is called a surd or a radical. Here a is called radicand, nth root is called radical sign, and n is called the degree of radical. Here are some examples for surds or root 3, root 5, cubed root 5, etc. Consider the real number root 5. It is also written as 5 power 1 by 2 since 5 is not a square of any rational number. 5 is a surd. Consider the real number 4th root 16. Since 16 is a square root of a rational number 4, 4th root 16 is not a surd.
Follow-up work.
Represent the decimal number 0.178 bar in p by q form. Represent the irrational number root 2 on number line. Find the variables x, y, z, whether it represents rational or irrational numbers. 1. X cube equal to 8. 2. Y square equal to 16. 3. Z cube equal to 0.08. Let us list out the properties involved in this chapter. You have successfully completed the chapter Real Numbers.